The fuss about P and NP revolves around one of the most significant unsolved problems in computer science and theoretical computer science. Whether every problem whose solution can be quickly verified can also be quickly solved. Here's a breakdown of what P and NP represent and why the question of whether they are equal is so important. P. Polynomial time. This class contains problems for which an algorithm exists that can find a solution in a reasonable amount of time, specifically in polynomial time. Polynomial time means that the number of steps the algorithm takes to solve the problem is bounded by a polynomial expression of the input size, e.g., n squared, n cubed, etc., where n is the size of the input. Problems in P are generally considered easy or tractable for computers to solve efficiently, especially for large inputs. Examples of problems in P include sorting a list, searching in a list, and finding the shortest path in a graph. NP, non-deterministic polynomial time. This class contains problems for which a proposed solution can be verified in polynomial time. The non-deterministic part refers to the idea that if you were given a correct solution, you could quickly, in polynomial time, check if it is indeed correct. Finding the solution itself might be much harder. Think of it like a puzzle. It might take you a long time to solve it, but once you have a completed puzzle, it's easy to check if it's correct. Examples of problems in NP include the traveling salesman problem. Given a list of cities and distances, is there a route that visits each city exactly once and has a total length less than a certain value? The Boolean satisfiability problem. Can a given Boolean formula be satisfied? And Sudoku. The big question, is P equals NP? The central question is whether every problem in NP can also be solved in polynomial time. In other words, if a solution to a problem can be quickly verified, can a solution to that problem also be quickly found? Why the fuss? Fundamental understanding of computation. Answering this question would give us a much deeper understanding of the inherent difficulty of computational problems. Practical implications. If P equals NP, it would mean that many currently hard problems, for which we only know slow exponential time algorithms to find solutions, could actually be solved efficiently. This would revolutionize fields like cryptography, optimization, artificial intelligence, and more. For example, breaking many modern encryption methods relies on the assumption that certain problems, like integer factorization, are not in P. If P equals NP, these encryptions could potentially be broken easily. If P nec NP, which is what most computer scientists believe, it would imply that there are fundamental limits to what computers can efficiently compute. We would know that for certain problems, finding a truly efficient algorithm is impossible. The Millennium Prize problem. The P versus NP problem is one of the 7 Millennium Prize problems posed by the Clay Mathematics Institute, with a $1 million prize for the first correct proof. This highlights its significance in the mathematical and computer science communities. In summary, the fuss is about whether the ability to quickly check a solution implies the ability to quickly find a solution. The answer to this question has profound theoretical and practical consequences. Most researchers believe that P nec NP, but a definitive proof remains elusive. This makes it a fascinating and important area of ongoing research. Do you want to delve into any specific aspect of P and NP further?